Good evening everyone, I am Mr. Ish. You're joining me for this third video here on the concept of area between curves. If you look over here very quickly, you know in this type of instance you have a clear designation of a top boundary curve and a lower boundary curve being this horizontal line. You got a top boundary curve which is an upside down parabola. In this instance, you know clearly the template to use is something like this. From the interval here A to B, you have a top boundary curve minus lower boundary curve with regards to dx, and you can take this through. You have an even function here. You can even use a shortcut if needed and just do everything from 0 to b and multiply by 2 and then 0 to b, and you'd have your this entire procedure over here and you take it through, and this would be a good shortcut. Looking there at that graph, you will find there will be situations where you can do multiple routes to achieve the same objective. The f function looks like a vertical line, the g function looks like a sine function. In this instance, the f function can look like a right boundary curve. The g function here in one instance can serve as a left boundary curve, and you could do a area determination between the curves with regards to y. You can look at everything from a lower limit in terms of the y up to this upper limit, which would very likely be a 1 for a sine function, and then you'd have your right boundary curve minus your left boundary curve. It would really be the f minus g dy. But the same question could also be done using the other route with regards to x, because you could see the g function in this instance can serve as a top boundary curve, but then the x-axis can serve here as a lower boundary curve, and we'll call that yb. In this instance, you can do from right here up to whatever this interval might be, a, we'll just call it a, most likely like pi over 2, because at pi over 2 sine function is a 1, we can even call it pi over 2. In this instance, the top of boundary curve is a g function, but the lower boundary curve is an x-axis, which is also y equals 0, so you can put a 0 here, which is meaningless, and you have this route. So you have multiple routes sometimes for a given question. You don't always have to resort to a cemented approach of doing things, so keep that in mind. In this video, we're just looking at 3 questions, after which the video will end, and that will be it for this. Let's look at this question. Y equals x minus 1 and y square equals 2x plus 6. We have to find the area between these two curves. We know one of these curves, which is the easier one, is just a linear line, y equals x minus 1. The other one appears to be a conic section, a parabola. I would like to proceed with this using the graphing technique, because the graphing technique will make it more meaningful for all of you who are watching. Y equals x minus 1 is easy. If you make x equals 0, you get minus 1 as one coordinate pair. If you make y equals 0, you get x is equal to 1. So you know you can graph this right here easily. Your linear line is basically this, not hard. We have to look at this. This right here is a parabola, and we may not have to complete the square because we already have it in the form y square equals. Look, y square is equal to, but we should at least make this into a presentable form, 2x, 2 parentheses x plus 3, and you can think about it in a parabola form, 4 times 1 over 2, x plus 3, y square is equal to 4px. But we're only doing this just to get the vertex. The vertex over here is minus 3 comma 0. Minus 3 comma 0, 1, 2, 3, and you know by no means is the origin involved over here. That's it right. Y square is equal to 4px. Here x is really an x minus h form. Anyhow, you can have a right facing parabola. We basically need to know what the intersection points will be, and our graph will look something like this. And we're looking at something right here in this graph form shading, but look, we basically have a right side and we have a left side boundary. So we have xr and we have xl, so we're looking at that other style of question. We have an intersection point over here we need to know, and we have an intersection point over here that we need to know, because these intersection points are going to give us our lower boundary limit and it'll give us our upper boundary limit right over here. We need to find those C and D. And how are we going to find these boundary limits? Simple. We're going to take each of these equations, we're going to solve them in place of x. Remember, when we're looking at an equation form, or let's say the area form of this style C to D, and then we're looking at xr minus xl then dy, well then these type of equations have to be written in terms of x. All of these have to be converted into x equals equations. Y equals x minus 1 becomes x is equal to y plus 1. Well, that's one equation form right here. This one right here has to be converted into x equals format. Y square minus 6 divided by 2 is equal to x. Well, this is my other equation. In these instances, you have to make the equations equal to one another and solve to get the intersection points. Y plus 1 is equal to y square minus 6 over 2. Take the 2 on the other side. You get 2y plus 2 is equal to y square minus 6. Bring everything together into a quadratic equation form onto one side. Y squared minus 2y minus 8 is equal to 0. Factor these out. Y minus 4 plus 2, y is equal to minus 2 comma 4. Limits. Here c is equal to minus 2, and then therefore d is equal to 4. Minus 2 and 4. You could get the coordinate pairs if you wanted minus 2. I'm not going to do it. And you can get the other one 4. It would be something x value here, x comma minus 2 and x comma 4. What are these values turn out to be? You would have to plug these minus 2 and minus 4s in place of these original equations and solve for x, and you can get these other coordinate pairs. But we don't need the coordinate pairs, we just need these limiting items, the lower limit and the upper limit. So now we have both of these equation forms. We have our limit from the lower limit minus 2 to the upper limit 4. Remember, equations here are in the form of x equals, right? Both of our equations are in the proper form. What's our right-sided equation? Well, it's y plus 1. What's our left-sided boundary? Equation boundary? It's y squared minus 6 divided by 2. And then in terms of dy. Open this up. 4 minus 2y plus 1. Y squared over 2 minus y squared over 2. I'm opening up the parentheses. 6 divided by 2 is a minus 3. Minus 3 with that thing becomes a plus 3 with a sign, and then you have a dy. Bring everything together, which you can. You have a y, 4 minus y squared over 2 dy. When you do the integration process of this entire polynomial, what do you get? You get a y squared over 2 plus 4y minus y cube over 6, and you have to do this from the minus 2 to the 4. Lower limit up to the upper limit. From lower limit minus 2 to upper limit 4. So we're going to plug in each of these y's. We'll put a 4 and then we'll minus that. What happens when we put in minus 2? So let's start working on this. I get a 6 over here. I get a plus 24 over here. Remember, you cannot be making a silly mistake over here, because then it ruins the entire outcome of our question. And then I get a minus 12 over here. So we just have to do all of this to lead to our final answer, minus 12. 6 plus 24 minus 12, and it shouldn't be too hard. And our final answer is 18, representing the area over here. This entire shaded area is represented by 18 units or 18 whatever. Whatever the units might be, units squared. We haven't specified units over here, but the area is going to be 18. So the combined question in terms of its area is completed. Not a difficult question, easy question, but this was another one of those instances where we had in a right side and left side boundaries, and we used vertical limits in terms of lower limit and upper limit being along the y-axis. So keep all of these specificities in mind when you're doing these questions. So now we should be getting quite comfortable with these type of questions, areas between curves. For this question before us, y equals 8x squared, y equals 3x squared, and then we have a linear equation and the condition that x is greater than or equal to 0. The best way to proceed with this, given that we might have 3 curves involved, is to graph it, because that'll tell you exactly in terms of a picture what we are dealing with, intersection points, what's on top, what's on bottom, what type of style we have. It'll help us do all of that. And I'm going to do a graph over here in an exaggerated style, because look at these parabolic graphs, 8x squared, 3x squared. You know, in terms of the vertical stretch, the a value, y is equal to ax squared. These a values would mean a steep incline. But we're going to do like a little bit of an exaggerated curve here just so we can differentiate. And we should make this into this form, 4x plus y equals 4. Then y is equal to minus 4x plus 4. Let's get the coordinate points. If x is equal to 0, y is equal to 4. If y is equal to 0, x will be equal to 1. Pretty much these graphs tell us that we're dealing with up and down type of graphs. So we'll be looking at something in this form, but we may have multiple intervals, or we may have 2 intervals only, or multiple integrals involved. Anyhow, we're looking at something of this form, yt minus yb, and then it'll be dx, these type of forms, looking at top and bottom boundary curves. Well, let's start our graphing process. 8x squared. I'm going to do exaggerated curves over here. I'll draw that as this. It should be more steep than that, but it'll originate here at the origin. And the fact that we're looking at x0, you know we can eliminate these parts of the parabolic curves or the quadratic curves, because here x greater than or equal to 0, we're only looking at positive values. Y is equal to 3x squared. You know it'll also be steep, but I'm going to make it look less steep. Let's draw the linear line, 0, 4 and 1, 0. 0, 4 and 1, 0. We could have probably done that a little better. So what are we looking at here in terms of the curve? or the area between the curve, we're looking at this area right over here. This area right here. We have an intersection point right here, which happens to be the origin. Intersection of these two is the origin. We have an intersection point right over here. And we have one intersection point right over here. We have to determine all of these intersection points. We know when we're looking at this origin, it's intersection point 8x squared and 3x squared. We can clearly tell, well, one intersection point is just 0, 0. We can easily tell that. Then we have to find this intersection point right here on the top. That intersection point here is between the 8x squared and the linear line. It's between the tug of war between 8x squared, and you know to find intersection points, you equal them out. It's a tug of war between 8x squared and minus 4x plus 4. Minus 4x plus 4. We're looking right here at this intersection point. Let's blow up that little segment we have, the area. Segment looks something like this. Right here. This little area is blown up over here, meaning I've zoomed in and we're magnifying this entire area right over here. So we're looking at this intersection point right over here. We know this intersection point right over here is 0, 0. We're looking at this top one. Well, we have to do work over 8x squared plus 4x minus 4 is equal to 0. Divide everything by 4. 2x squared plus x minus 1 is equal to 0. Factor it out. Plus 1 minus 1, x is equal to minus 1 and 1 over 2. You can throw one of these values out because here, this condition, x is greater than equal to 0. You can only keep a positive value. So we have to keep positive value 1 over 2. Alright, so we know here the x coordinate is 1 over 2. We have to find the y coordinate of this pair, of this intersection pair. How are you going to find that? Just put 1 over 2 right in this equation right over here. Or you put 1 over 2 in here. You'll get 2. 1 over 2 comma 2. We basically don't need to find these coordinate pairs. All we need to do is find these x-axis values only. Now let's look at this intersection point, which is this point right over here, which is made up of the 3x squared and the linear line. The tug of war between the 3x squared and the linear line. 3x squared is equal to that linear line minus 4x plus 4. It's going to be a quadratic equation which will generate over here. 3x squared plus 4x minus 4 is equal to 0. You can factor it out. It's not hard. When you factor it out, you're going to get 3x minus 2 and you'll get x plus 2 equals 0. You get x is equal to 2 over 3 and x is equal to minus 2. Let's bring it right here. X is equal to 2 over 3 and x is equal to minus 2. We can only keep the positive value 2 over 3. Only the positive value. You put 2 over 3 over here. Let's find the actual coordinate pair. How do you find the coordinate pair? Put 2 over 3 here or put 2 over 3 and solve for y. If you put 2 over 3 over here, you'll get 3 times 4 over 9. The 3 and the 9 will cancel out such that you get a 4 over 3. That's your coordinate pair over here. But we're only looking at the x-axis values, or should I say in a better way, we're only looking at the x aspect of that coordinate pair, because I'm going to show you why. We have an interval now developing like this, from 0 to 1 over 2, then 1 over 2 to 2 over 3. So our area is going to be generated like this, and we don't have any even functions playing out over here. The first one is going to be from 0 to 1 over 2, 1 over 2, right here. From 0 to 1 over 2, we have a top curve and a bottom curve. What's the top curve over here? The top curve is this 8x squared. 8x squared. What's the bottom curve? Here's my top curve, and you know here's a linear line going this way. So between the interval 0 to 1 over 2, see 1 over 2, 0 to 1 over 2, we have 8x squared minus 3x squared. The lower curve is 3x squared, and you know this is in terms of dx. Then we have to do this plus because we have two sets of integrals. They have to add up. Then in the second interval from half to 2 or 3, you're only looking here at the x coordinates here. So the second interval is from 1 over 2 to 2 over 3. From here to here, this linear line, from this point to this point, you can see that there's this linear line that forms the upper boundary. So you can do minus 4x plus 4. That's the upper boundary right here. And what forms the lower boundary? The 3x squared minus 3x squared, and let's put dx over here. So that right there is our equation form we have to look at. It's a little clustered here, but we can read it out. So let's start simplifying this. You basically have from here 1 over 2, 0, you have a 5x squared dx. And then you have from here 2 over 3 up to 1 over 2, you have a minus 3x squared minus 4x minus 3x squared minus 4x plus 4 dx. That's what we have. And this right here will become a 5x cubed over 3 here, and from half to 0. Minus 3x cubed over 3 will become a minus x cubed. Alright, and we can have this over 2 over 3 and 1 over 2. We can separate these individually among their definite intervals. We'll have a minus 4x squared over 2, which is a minus 2x squared, right? Over 2 over 3 and half. We'll have a plus 4x over it's 2 over 3 and 1 over 2. We're going to run, as you know, upper limit, lower limit into each of these. I'll publish the values right over here on the bottom. Let's put the value over here by adding all of these numbers. And our area is 0.31482. So let's publish here the value. A is equal to 0.31482. Area of this entire, you can say a triangular, but it's a curved triangle, but that's what it is. And that question has been done. So it's a slightly tricky question, but not hard. It was probably more cumbersome, especially here. You could have kept everything here in terms of fractions and come up with a good fraction answer, but it might have been too much work to keep doing fraction algebra all the way across. Using the calculator simplifies it. And looking at only the x coordinates of each of these pairs gave us our intervals 0 to half, and then half to 2 or 3. And then for each of those intervals we had a top and a lower boundary, a top and a lower boundary, and we carried it through using this template here, but 2 integral parts, and it was done. Let's look at this question. Y squared is equal to x plus 1, y is less than or equal to 1, y is greater than or equal to 0, and x is equal to root y. We have a bunch of things going on over here, and until we don't graph it, it'll be difficult to see what we are dealing with in terms of areas between the curves. When I look at this x is equal to root y, I'm also thinking y is equal to x squared. All they've done is here solve in terms of x. So I know they're eliminating the negative values in terms of the x. So we're just looking at something like this, which would be root y, but you're only looking at the positive aspects of this parabolic style curve. These things would be the same here with regards to one another. Graph-wise they're the same, and that's exactly what you see over here. Y is greater than or equal to 0. You have this x-axis line, you're looking at values above it, but y is less than or equal to 1. Let's draw this. Y is equal to 1, and here we got y equals 0. We're looking at values here in terms of below 1 line, values below this line, and we're looking at values above this y equals 0 line. What about this? Y squared is equal to x plus 1. That looks like a parabolic iconic section. You got here of something in the form y squared is equal to 4p times x minus h. You know clearly you have a vertex here of a minus 1 comma 0. Minus 1 comma 0. We just estimate our vertex over here, and we just draw this upward. If x was equal to 0, you know you clearly will have a y-intercept of 0 comma 1. So this thing should have a intercept over here of 0 comma 1. You can tell that clearly from the graph and from the equation. If you make in that equation y squared is equal to x plus 1, if you make x 0, you get y squared is equal to 1, then y is equal to plus and minus 1, but we're not really looking at these negative values here, because here you would have a 0 comma minus 1, but we're not looking at that. Why aren't we looking at that? Because we're looking at values of y greater than or equal to 0 and less than or equal to 1, so it kind of eliminates this lower graph. So what you end up having here is just the 0 comma 1 intercept of this parabola plane. What are we looking here in terms of the shaded area? We're looking at all of this area right over here. In terms of the shading, all of this area right here. You can clearly see what we have over here. We have a right side curve and we have a left side curve, and that's the type of question we're looking at. Something of this form, C to D, and we are dealing with a right side minus a left side, and in terms of dy. So what are our equations which are going to play here in terms of dy? We already have our C and D intervals laid out. This 0 and 1 clearly gives us our interval. Here's my C interval and here's my D interval. Lower limit and upper limit. Here's my lower limit C, upper limit D. So I'm looking very clearly at this from a 0 up to 1 in terms of vertical 0 to 1. Now all we need to know is our right side and the left side. The right side curve is this one right over here, which was root y. Here the equation must be x equals form, and we are looking at this x equals form right here, but we're not looking at it over here. This has to be modified, and that equation becomes x is equal to y squared minus 1. Here's our other equation, and that's our left side equation, minus y squared minus 1 and dy. Let's look at this. We have 0 to 1. We should write this in power form. 1 over 2 root y is y to the 1 over 2 minus y squared plus 1 dy. Integrate all of this, it's easy. 1 over 2 becomes y to the 3 over 2 divided by 3 over 2, and our question is easy because of this 0. 0 will be meaningless. All you'll have to do is just put 1s in place of your antiderivatives and you'll easily get your answer. Minus y cubed over 3 plus y. What you end up getting over here, when you simplify all of this, is 2 over 3 y to the 3 over 2 minus y cubed over 3 plus y over the interval 1 and 0. You're basically looking at now just 2 over 3 because you can put 1s in all of these. Taking the zeros from them is meaningless. 2 over 3 minus 1 over 3 plus 1. 2 over 3 minus 1 over 3 is 1 over 3. 1 over 3 plus 1 is a 4 over 3. And this right here is our clear area of this curve. So area over here is equal to 4 divided by 3, which is 1.333 repeating. It does not look like a large number in terms of an area, but who cares? And the graph is never drawn to scale, but it tends to be slightly accurate in terms of its depiction. But this right here, 4 over 3 being the area of this curve, bounded by these lines, is true. We have this y equals 0 delimiting the lower interval. We have y equals 1 highlighting the upper interval. We have this right side curve, which is the root y, and then we have this left side curve, which is this parabolic extension. And these things define the extent of the shading between the curves.